All right, so in the previous video, we looked at the backward induction argument. And we'll continue with the solution concepts for extensive form games. And in this video, we're going to look at subgame perfect Nash equilibrium. So the backward induction procedure that we looked at in the previous video can be applied to only a limited class of games. We must start from a different foundation here to represent sequential rationality. So one direction is to start with the concept Nash equilibrium and then think of refinements based on the consideration of sequential rationality. So in other words, for any given game, we can calculate all of the Nash equilibria and then remove the ones that violate sequential rationality. To do this, we need to define what it means to violate sequential rationality. So let's consider, first the notion of a subgame. So given an so let's highlight it. So given an extensive form game, a node X in the game tree is said to initiate a subgame if neither X nor any of its successors are in an information set that contains nodes that are not successors of X. A subgame is the tree structure defined by such a node X and its successors. So this is a definition of what is a subgame. So next, let's consider an extensive form game to understand how to identify a subgame. So here we have a three-person game. There are three players in the game. So before we look at this game, let's just try to understand the subgame perfection. So you take any node X in an extensive form, right? And then examine the collection of nodes given by X and its successors. If there is a node Y that is not a successor of X, but is connected to X or one of its successors by a dashed line, then X does not initiate a subgame. In other words, once players are inside a subgame, it is common knowledge between them that they are inside it. Subgames are self-contained extensive forms, meaningful trees on their own. Subgames that start from nodes other than the initial node are called proper subgames. Keep in mind that in a game of perfect information, every node initiates a subgame. So here in this game that we have, it's a three-player game, as you can see. The initial node initiates a subgame. So initial node is here. It initiates a subgame because the entire game is itself a subgame. So you're looking at this whole game here. This entire game is a subgame of itself, right? Node Y also initiates a subgame. So where is node Y? Here. I didn't write it down. So node Y initiates a subgame because Y is not tied to any other nodes by a dashed line, and all of Y's successors are terminal nodes. Node X here, this one, in contrast, does not initiate a subgame because one of its successors node G over here is in the same information set as a node that is not one of its successors, that is node W. In other words, starting from node X, there is a contingency in which player 3 does not know whether he is at a successor of X. So by the same reasoning, neither G nor W initiate a subgame. So therefore, this extensive form game has only two subgames. First one is the entire game, and the second one is the proper subgame starting at node Y. So this is another subgame. All right, so next let's consider the refinement of Nash equilibrium that incorporates sequential rationality by evaluating subgames individually. So what is a subgame? So a strategy profile, so let's highlight it with a different color. A strategy profile is called a subgame perfect Nash equilibrium if it specifies a Nash equilibrium in every subgame of the original game. So the basic idea behind subgame perfection is that a solution concept should be consistent with its own application from anywhere in the game where it can be applied. Because Nash equilibrium can be applied to all well-defined extensive form games, subgame perfect Nash equilibrium requires the Nash condition to hold on all subgames. So let's consider an extensive form game to understand the subgame perfect Nash equilibrium, how you can find that. So consider the game we have in this here on the slide. Let's use a different color here. So this game we are looking at. So keep in mind that this game has one proper subgame, which starts at the node reached when player 1 plays up at the initial node. So this is a proper subgame. And then the whole game is itself a subgame. So there are two subgames here, right? But one is proper, that starts at, node that follows a strategy U for player 1. All right. So we have to evaluate two subgames here, the proper subgame and the entire game. So because strategy profiles tell us what the players do at every information set, each strategy profile specifies behavior in the proper subgame, even if the subgame would not be reached. So for example, consider a strategy profile DAX. So strategy profile DAX. If this profile is played, then play never enters the proper subgame. But DAX does include a specification of what the players would do conditional on reaching the proper subgame. So in particular, it prescribes action A for player 1 and action X for player 2. So let's continue with this game, and you will notice that there are two normal form games that I have drawn here. This one represents the whole game, and this one is the proper subgame, right? So we converted this, extensive form game into the normal form games. The 4x2 dimension game, this game represents the whole game, and this the 2x2 game represents the proper sub game that's circled here in red. All right. So if you look at this, the whole sub game, right? The whole game itself, right? So in this game, if you want to find the pure strategy Nash equilibrium, so here we have 3 of them. So we have this one, UAX, this. Then we have DA and Y. So this, and then DB and Y. So we have 3 pure strategy Nash equilibria in this game. Okay. But not all of these strategy profiles are subgame perfect. To see this, let's look at the proper subgame, right? And it has only one Nash equilibrium, AX. So in this proper subgame, we have just one Nash equilibrium, AX. The strategies DA and Y and DB and Y are not, so this and this, they are not subgame perfect because they do not specify Nash equilibria in the proper subgame. So in particular, DAY stipulates that AY be played in the proper subgame, but AY is not an equilibrium. Additionally, DBY, this one, specifies that BY be played, B and Y be played in the subgame, but B and Y is not an equilibrium. So therefore, there is only one subgame perfect equilibrium in this game, and that is UA and X. So the subgame perfection concept requires equilibrium at every subgame, meaning that if any particular subgame is reached, then we can expect the players to follow through with the prescription of the strategy. This is an important consideration, whether or not a given equilibrium actually reaches the subgame in question. So look at Nash equilibrium DA and Y, DA and Y, right? It entails a kind of threat that the players jointly make to give player 1 the incentive to select D at his first information set. But the threat is not legitimate, not credible. In the proper subgame, AY is about as stable as, anything you can imagine. So player 1 has the strict incentive to deviate from this prescription. So there are a couple of things that are worth pointing out here. First, that subgame perfect equilibrium is a Nash equilibrium because such a profile must specify a Nash equilibrium in every subgame, one of which is the entire game. So therefore, we speak of subgame perfection as a refinement of Nash equilibrium. The second point that I would make here is that for games of perfect information, backward induction that we discussed previously yields subgame perfect equilibria. Okay,